In this video, let's define the conditional distribution and conditional traits of one random variable given another random variable. Often, because of the dependence between two random variables, learning the realization of one may provide information about the other. And therefore, we call the revised distribution of the later random variable after learning the realization of the former random variable, the conditional distribution. What is the definition of conditional distribution? We can define the conditional distribution for discrete random variables at least when the conditioning event has non-zero probability. So suppose that the probability that big X equals little x is positive, then we can define the conditional distribution of y given x equals little x to be this. The conditional distribution is written in this form. So the notation for it is little f with the variable of interest, which is y, with a vertical line followed by the conditioning variable x. Parenthesis, the value of y that we evaluate the distribution at, and the value of x that we are conditioning at. So that is the notation for the conditional distribution of y given x equals little x. And that is defined to be the probability that y equals little y given that x equals little x. And this, notice that y equals little y, x equals little x are two events. So let's say this is A and that is B. That's PA given B. And we can use the conditional probability formula to find that this conditional probability is probability of both A and B divided by the marginal probability of just B. And written again as PMFs, this is joint PMF of x and y evaluated at little y and little x divided by the marginal probability mass function of x evaluated at little x. So this is the conditional probability formula. And in this definition, this x is called the conditioning variable. So this is the modified or revised distribution of y after we learned that the realization of x is little x. Now consider an example, which is the same medical expenditure example we considered in the last video. There are two variables, x and y, and their distribution, their joint distribution and marginal distribution are described in this two-way table. Now let's calculate the conditional distribution of no insurance medical expenditure, which is x in this table, given that the medical expenditure under insurance, and that is y in this table, given that y equals 600. So in this example, the conditioning variable is y. So that is the conditioning variable. And the variable of interest is x. So what is the conditional distribution of x given y? Given that y equals 600. We can see from the table that when y equals 600, the probability that x equals 0 is 0. So x cannot equal to 0 when y equals 600, but x could equal 500 or 50,000. So x has two values. The probability that x equals 500, given that y equals 600, is given by the joint probability 0.19 divided by the marginal of the conditioning variable at the value 600, which is 0.2. So 0.19 divided by 0.2, which is 19 divided by 20. This is if little x equals 500. And the conditional probability of x being 50,000 is given by 0.01, the joint PMF, divided by the marginal of the conditioning variable, 0.2. So 0.01 divided by 0.2. That's 1 over 20. This is if we are considering the value of x that's 50,000. Notice that this PMF of x given y equals 600 is a distribution, is a probability mass function. Why? Because the value of this function are all non-negative, they're all positive, and the sum of the two values equals 1. So 19 divided by 20 plus 1 divided by 20 is 1. And that satisfies the requirement for probability mass functions. So conditional probability mass functions are probability mass functions. So this is, we're talking about the same thing here on this slide. Conditional distribution is a distribution in general. So for any realization little x of x, now we are switching the rows of conditioning variable and variable of interest again. Now x is the conditioning variable. For any realization little x of x, f of y given x is a distribution of y, is a distribution. So it satisfies the requirements for distribution functions. So satisfy f of y given x at any y value, and this is non-negative. And it also satisfies sum of little y over all the possible values that y can take. The conditional distribution, conditional PMF equals 1. So this is because sum of the conditional probability mass function equals sum of y joint probability mass function divided by the marginal of the conditioning variable. But remember how we get the marginal from the joint probability mass function. We get the marginal of x by summing over all the y's, summing over the y for the joint probability mass function. So the numerator is also the marginal of x that is equal to the denominator, therefore that is 1. The conditional distribution is also a distribution. Since it's also a distribution, we can talk about it as the same way as we talk about unconditional distributions, and it has traits. One particularly important trait for this course is conditional expectation, or sometimes we call conditional mean. Suppose that the conditioning variable the probability that the conditioning variable equals little x is positive. The conditioning event is a positive probability event. The conditional mean of y given x is can be defined the same way as we define the unconditional expectations. So that is the weighted average of all the y values with the weight given by the probability mass function. And here, we still consider a weighted average of all the y values. The probability mass function is the conditional probability mass function of y given little x, given x equals little x. So that is the definition of conditional mean. Similarly, we can also define the conditional variance of y given x equals little x. So the conditional variance is the average of the deviation from the mean, and now the mean is the conditional mean. Squared weighted by the conditional distribution. Right, so it's important to note that this mean considered here is a conditional mean. This is the conditional variance of y given x equals little x. Similarly, we can also define the conditional standard deviation of y given x equals little x, and that is nothing but the square root of the conditional variance. Next, let's consider an example where we calculate the conditional traits. In this example, suppose that x is a random variable dividing the population into groups. X equals 0 if the randomly selected person is a female, and x equals 1 if that person is male. Now let y be another variable like that, but it groups the population in different way. So y equals 0 if the person votes for Trump, and y is 1 if the person votes for Biden in the general election. So the distribution of x and y can be described in this two-way table. Suppose that their joint distribution can be described in this two-way table. And in this two-way table, we have already calculated the marginal distributions of x and y. And we also have the joint probabilities. From this two-way table, we can figure out the conditional distributions. One interesting conditional distribution is women's vote distribution. And what is this distribution in mathematics? That is the distribution of y given that x equals 0. X equals 0 stands for women. So f of y given x equals 0, that's not the notation we use, f of y given that x equals 0 has two possible values. Because y has two possible values, y could take 0 or 1. Now, because we're considering women's vote, that's x equals 0, so only the first row matters. We consider the distribution described in the first row. The conditional distribution of y, given x equals 0, is given by 0.1 divided by 0.5. That's 0.2. If we are considering the vote for Trump, and it is 0.8 if y equals 1. So clearly that is a legitimate distribution. The probability mass function, the value of this function is non-negative, and it's sum to 1 for all the values of y. And similarly, for men, we can also figure out the men's vote distribution, which is f of y given x equals 1. Now we can also, we could write this in a table. So y has two values, 0 and 1. Probability that y equals 0 given x equals 1 is given by numbers in this row. That's 0.3 divided by the marginal of x, 0.5. So that's 0.6. And similarly, this is 0.4. So this is how you figure out conditional distribution from the two-way joint distribution table. And we can use this table, these marginal distributions, to figure out the expectations, conditional expectations. The conditional expectation of y from the first conditional distribution is also called the women's probability of voting for Biden, and that is expected value of y given x equals 0. We use the distribution given in this table. So 0 times 0.2 plus 1 times 0.8, and that is 0.8. And men's probability of voting for Biden can be written, can be calculated in a similar way using this conditional distribution table. So that is 0.4. We can also calculate the conditional variance of the vote distribution for both women and men. For women, the conditional variance of y given x equals 0 equals variance of y. Remember, the variance of y can be written as expected value of y squared minus square of the expected value. This is a formula we learned for unconditional distribution, but it holds for conditional distribution as well. And this is particularly easy to use in this case because the square of y is the same as y. So expectation of the square of y is the same as expectation of y. And that gives us 0.16. Similarly, we can do this for men. And that is 0.4 minus 0.4 squared, that's 0.24. So that's conditional variance of women and men.